Greetings, everybody. Let's begin our discussion of trigonometric substitutions. So when we're talking about integrals in which we could do a trigonometric substitution, so this is going to be pretty similar to our U substitutions, they're really going to kind of come in three different forms. So maybe an integral where we are doing something like the square root of x squared minus 4. They could come in a form where we're doing something like 1 over the square root of 9 plus x squared. Or they could even come in the form where we are doing something like 3x times 4 minus x squared to the 3/2 dx. Now, what kind of separates each one of them? So what separates them and what makes them similar as well is the fact that when we look at these integrals, we are seeing something that either reminds us a little bit of what we would have with our Pythagorean theorem. So with our Pythagorean theorem, imagine that we've got a right triangle. And so we've got a side x, we've got a side a, and then we've got x squared plus a squared. On that one, square root of that. Or we've got a triangle, in which case we've got an a, we've got an x, and then we've got a square root of a squared minus x squared. Or kind of the last one, we've got a right triangle, in which case we've got an x, we've got an a, and then we have a square root of x squared minus a squared. So these three different situations kind of corresponding to what we're seeing in our integrand of each one. So when we have an x squared plus a squared, we're really kind of thinking of this kind of substitution. When we've got an expression involving a constant minus x squared, now we are in this situation. And finally, when we're in the situation where we have x squared minus something, then that is really corresponding to this. So we've got three different situations where they're all similar in that they're all involving right triangles. And we've got those three separate cases that break up for dealing with those right triangles. So let's kind of jump into seeing how we deal concretely with some of these examples. All right, so let's begin with supposing that we were asked to evaluate an integral of dx over the square root of 4 plus x squared. And so in this case, kind of the right triangle that we're going to be dealing with is the situation in which we know that one side is going to be x, one side is going to be 2, and so our hypotenuse ends up looking like the square root of the sum of the squares of our sides. So we get the square root of x squared plus 4. Now, in this case, what we're going to imagine is let's pick an angle. And so what we have for that angle, we actually have, looking at our trig substitutions now, what we have, if we look at the tangent of theta, that is going to be our x over 2. Okay, and so what we have then with x is 2 times the tangent of theta. And now when we do the substitution, this is kind of the u substitution that we're going to have if we wanted to then do, so looking at our integrand, our dx is going to be 2 times the derivative of tangent, which is going to be secant squared of theta d theta. Now, when we do the substitution, into our expression, what happens there is we now have the integral of dx being our 2 secant squared theta d theta. On the bottom, we have our square root of 4 plus x squared, so that's 4, plus x squared is going to be 4 tangent squared theta. And so we have the integral of 2 secant squared theta d theta divided by, if we factor out a 4 from that, then we will have a square root of 4 down here, and then we'll have a square root of 1 plus tangent squared. So now using our trig identity, we see this as 1 plus tangent squared is really just a secant squared. So we've got 2 secant squared of theta d theta. Square root of 4 becomes 2. This becomes the square root of secant squared. And so when we then simplify our expression, what we have is the integral of dx over the square root of 4 plus x squared becomes our integral of 2 secant squared theta d theta divided by 2 secant of theta. So one of our secants is going to cancel, our 2's cancel, and we just have the integral of secant theta d theta. Okay, which now we're going back to the trigonometric integrals that we did just before, or you can remember your trig identities or formulas from our trigonometric integrals and kind of remember the trick that we had there with secant. With secant, we multiplied the top and the bottom by secant plus tangent. And what that did for us was to give us secant squared of theta plus secant of theta tangent of theta on top, secant of theta plus tangent of theta on the bottom, which if we did a u substitution with u equal to secant theta plus tangent theta, gave us something that looked like 1 over u du. And so we had a natural log, absolute value of u, or a natural log of the absolute value of secant of theta plus tangent of theta. Now this gets us back to theta, but it doesn't necessarily get us back to our integral, and so we kind of have one more step beyond where we've got our integral of dx over the square root of x squared plus 4. We said that looks like the absolute value of the secant of theta plus the tangent of theta plus c. Well, now we remember our right triangle that we use to kind of form all of this. Okay, so our expression was 4 plus x squared. So we had an x, we had an a, actually the a being really 2, sorry. Messed that up again. So 2, and so that our hypotenuse was going to be square root of x squared plus 4. And so our angle theta, we had that the tangent of theta was going to be x over 2. And also from this triangle, if the tangent was going to be x over 2, our secant of theta, which was 1 over our cosine of theta, was going to be the hypotenuse over the adjacent, and so that one looked like the square root of x squared plus 4 over 2. And so what we have there, now we can come back using this triangle back to our integral, and we can replace this with our corresponding expressions in x. Secant of theta becomes square root of x squared plus 4 over 2 plus tangent of theta becoming x over 2 plus our arbitrary constant. And so our trigonometric substitution, just going that way, we just find the right triangle that's going to correspond to our expression underneath our radical, and then we go from there. So let's, that's probably a good stopping point for this one. Let's come back with more examples again and kind of delve into this just a little bit further. See you guys then.